one guy who's in lab today until 6:30. So he's taking his quiz at 6:30. That's going to be horrible. Anyway, all right, so we're going to talk about black holes, all right? And I'm going to tell you some things about black holes which you might or might not have known, but I'm definitely going to show you how to deal with black holes. And so let me start with the metric for a black hole, which is, of course, the same metric that we've been using. It's called the Schwarzschild metric. -1 minus 2gm over r dt squared plus the inverse of that times dr squared plus r squared times d omega squared, where this is just the standard metric term for the spherical polar angle contribution. Okay? Now remember, this is a spherically symmetric solution to the vacuum form of Einstein's equation, that is, the Ricci tensor vanishes. All right? And we ended last time with me first and foremost pointing out that Newtonian mechanics predicts a black hole, but that black hole is actually shit. It's not anything like an actual black hole. And then I also pointed out that this is not just the metric for a black hole, it's also the metric for any spherically symmetric source, okay? The big difference is that this is the metric all the way down to r equals 0, where it blows up. However, if you're dealing with a spherically symmetric source of radius r, this is only good to radius r. Beyond that, you have to do an interior solution, okay? And what's more, the two values of the radius, that's r equals 0 and r equals 2gm, those are inside of any spherically symmetric source that actually exists. Okay, so the Earth has a value of r which is equal to 2gm, but it's inside of the Earth, so this isn't the appropriate metric. Okay? But for a black hole, r equals 2gm is obviously outside of it because the only interior of a black hole is the singularity. So this is why black holes are special. Okay, now, clearly, something goes wrong when r equals 2gm and when r equals 0. Okay? But we have to ask ourselves first and foremost, things look weird, but are they really and truthfully weird? Okay? I mean, obviously, if r is 0, then this term is blowing up. And if r is 2gm, then this term is blowing up. Okay? So we have metric terms which are going to infinity at both of these values. But is that truly a problem? Okay? And that's the first question we have to ask and answer. Are these points of singularity? Okay? So in order to help with answering the question, I'm going to start by thinking of a more familiar example, which is just Euclidean space. This is two-dimensional infinite space, which has no problems. There's nothing weird, it's not curved at all. Okay? Now what we're going to do is we're going to describe the space in terms of polar coordinates. And hopefully you're all aware that this means that the metric of the space is 1, 0, 0 r squared. And moreover, the inverse metric of the space is 1, 0, 0, 1 over r squared. Okay? Now, this is a different example than this, so I'm only going to talk about this for now, and then I'll come back to this. At what value of r does the metric or the inverse metric pose a problem? Jared? 0. Yeah. See? It's that easy. Yeah, at r equals 0, this guy blows up. And at r equals 0, this becomes degenerate. This is 1, 0, 0, 0. Which is not a very functional metric. Okay? So when r equals 0, Gij is degenerate, we should ask ourselves. The metric is becoming degenerate. The inverse metric is blowing up to infinity. Does that mean that there's a black hole on this space? Hell no. What's the space? It's just a flat plane. It's an infinite flat plane. That's it. There's nothing interesting going on. Okay? The moral of this story is just because something weird is happening to the metric or the inverse metric, that does not necessarily mean that something weird is happening in the space. Okay? To systematically handle this, we should do two things. And I will write them down here. First of all, remember that the metric can change with different coordinates. Okay? What we really want to investigate to figure out whether this space is curved or singular or whatever is what we want to figure out is invariant statements about the geometry. So for R2, we know that it is flat. That is, the Riemann curvature tensor of this space is equal to what? It's tensorial form of 0, but yeah, it's 0. Okay? This will not change if I change coordinates. If something is equal to 0 and this thing is a tensor, I can change the coordinates to whatever I want, and all it's going to do is it's going to change with a bunch of these. But if this is 0, then the whole thing is still 0. So changing coordinates won't change the fact that this is 0. Of course, we can take Rij, K, L, and we can derive many other invariants or tensors from it. We can derive the Ricci tensor, we can derive the Ricci scalar, and then there's others that we can derive. Okay? In fact, we can do a quadratic of the Riemann tensor with itself. So we could ask about this. Oops. Okay, so there's all these things that we can derive, but since we're starting out at 0, all of these are 0. There's going to be an important catch on that in a little bit, okay? So, in order to explore whether a space is doing something weird or not, we should not look at the metric, because the metric is not 0. Rather, we should look at things which are 0 if the space is trivial, and not 0 otherwise, because these statements are coordinate independent. Now, there's option B. Option B says, screw it. Change coordinates. Why not? I mean, this is just in r theta, but we know that if we use x equals r cosine theta and y equals r sine theta, then our metric becomes what? Sean?
1, 0, 0, 0, or no?
So this is in r theta coordinates. If I do a transformation to this x, y coordinate system, what will the metric become?
1, 0, 0, 1.
Yes. This is the Cartesian description of flat space. It's just the identity. And in fact, it's the same as the inverse. Okay? Now, clearly, even though it looks like r goes to 0 is doing something weird in this geometry, it ain't. So we call this a coordinate singularity. That is, you're getting a singularity, something's going to infinity, but it's just because of the coordinates you're using. It's not that the space itself is going singular in its curvature. Okay? Now this is an important point because we have two places where this metric is going whack. And we should ask ourselves, are these true singularities or are they coordinate singularities? Here it's obvious, here it's not so obvious. Okay? So, let's take approach A, okay, on the Schwarzschild metric. So if I take approach A, what I find is the following. Well, first of all, remember that that curvature measure, r mu nu, is automatically 0 because this is the solution to this form of Einstein's equations. Of course, if the Ricci tensor is 0, then obviously the Ricci scalar is 0. But this means if we're going to look for a tensor which is describing the curvature, we have to go back to the whole deal, the Riemann curvature tensor. Okay? And what we find is the following. Actually, let me back up. Let me back up and say something a little bit different about this point, okay? So I said earlier that the metric is not 0 and it transforms, okay? This thing is 0, but it transforms, okay? If you transform it, it's still 0, okay? What we would love, though, is a coordinate invariant statement. That is, no matter what coordinate system you use, the result is unchanged. Versus, if I change coordinates, it'll change the result. If the result is 0, then it will remain 0. But if it's not 0, it might change. That's my point. So what we're perhaps after is coordinate invariant combinations of these things. And so for coordinate invariant combinations of these things, we might consider the Ricci scalar, or we might consider contractions of the Riemann tensor with itself. Okay? Something like that, right? Because these are invariants, they have no free indices, so they don't transform at all if you do a coordinate transformation. Okay? Now, back to here. Since the Ricci tensor vanishes, this coordinate invariant obviously vanishes. But this is not the only coordinate invariant we can imagine. And it turns out that all other coordinates invariants vanish except for this one. That is r mu nu rho sigma, r mu nu rho sigma. That is, I take the Riemann curvature tensor, I raise the last three indices, that's the first term, and then I lower the first index, that's the second term, and then I contract these fully, so this is a scalar. This comes out to be 48 g squared m squared over r squared. Now, like I said, all other curvature invariants are 0. This one's not. Now I'll ask you, which of these two is problematic?
0.
Yeah, r equals 0 is problematic, clearly. R equals 2gm, it's just a number. Who cares? This is a measure of the curvature, folks, and you're in a curved space. So the fact that at r equals 2gm, that's not 0, that's not scary. You're in a curved space. Okay, some curvature you should have some invariant which measures the curvature. What's good is that at r equals 2gm, this is not diverging. Whereas for r equals 0, clearly this is diverging. Okay? All right. So we know that r equals 2gm is a coordinate singularity. It is not a true curvature singularity. That means that we should be able to take approach B. That is, we should be able to rewrite the metric in terms of a different set of coordinates. And in that new set of coordinates, it should be obvious that r equals 2gm is not a problem. R equals 0 will remain a problem because r equals 0 is a true singularity. Okay? So now we're going to turn to better coordinates. Okay. So what we're going to do is we're going to transform from what is often called the Schwarzschild coordinates into a new set, which is really just replacing t with something else. And these are called the Eddington Finkelstein coordinates. And you might wonder, why does he write out those names? Why doesn't he just put S and EF? And I have to write the name Finkelstein on the board at least once, because he was at Georgia Tech when I was there, and I took classes from him. Boom! Yeah, it's the most famous physicist I know. No, he's actually not the most famous physicist I know, but anyway. He's a very cool guy. So the coordinate transformation is V is T plus R plus 2GM times the natural log of R over 2GM minus 1. And it's the magnitude of this. It's the natural log of the magnitude of R over 2GM minus 1. Okay? Clearly we can invert this to find T as a function of V and R. And the reason we want to do that is because if we want to transform these coordinates, I need something to replace T by. I replace it by this, but of course if we're going to replace it, we need to replace dt, not t itself. And dt turns out to be dv minus 1 minus 2gm over r inverse dr. Okay? So this might have looked like a completely, where the hell did they get that coordinate transformation? This might make a little more sense, because clearly this factor is Mr. Problem factor here. Okay? So now all we have to do is take this and plug it in for that right there. That's the only place it appears in this metric. Now I'm going to write what we get, but hopefully it's kind of obvious. Okay. So here we go. ds squared is minus 1 minus 2gm over r dv squared plus 2 dv dr plus r squared d omega squared. Okay? The technical name of this is the Schwarzschild geometry in Eddington-Finkelstein coordinates. I'm just kidding. The geometry is the Schwarzschild geometry. If I change coordinates, it does not change the geometry. The geometry just physically exists. Coordinates are just our way of describing it. I can use any coordinate system I want. So this is the same geometry as this, just written in a different coordinate system. Okay? Now, does anyone notice anything nice about this?
Is the 2GM, or the 2GM singularity still?
Yeah, the 2GM singularity is gone. might say, oh, what about the inverse metric? Trust me, the inverse metric is not as easy to find because this has a cross term. Okay? But in reality, the r equals 2gm coordinate singularity has been resolved. Okay? Nothing is going to infinity as r goes to 2gm. Of course, r equals 0 is still problematic. Okay? But this all sits in harmony with what we got when we calculated the coordinate invariant measures of curvature. The coordinate invariant measure of curvature was going to infinity for r equals 0, but it was just a constant finite number for r equals 2gm. So we just resolved that by a change of coordinates. Now, Schwarzschild coordinates go haywire at r equals 2gm. Okay, remember, when r is equal to 2gm, this guy's blowing up. But they're good otherwise. That is, you can be at r equals greater than 2gm, and in which case this is fine. Or you can be inside of r equals 2gm, and then these are also fine. It's just at the point r equals 2gm or at the point r equals 0, that's where you have a problem. Okay? Eddington-Finkelstein coordinates are good everywhere except r equals 0. In particular, and this is what's the most important part of the story, we know that r equals 2gm is going to define for us the event horizon of a black hole. And one of the most interesting facets of black holes is not the singularity at the center. That is just something we can't describe, not with this theory. This theory blows up. However, the event horizon itself is perhaps the most amazing part of a black hole. There's lots of interesting behavior that it gives forth, okay? However, with the Schwarzschild coordinates, you can start outside of the black hole, but you can't use this metric to describe passing through the horizon, because this metric goes crazy at the horizon. This one, Eddington-Finkelstein coordinates, are perfectly well behaved through the horizon. So these are going to provide us with a consistent description of moving through the horizon, which is what we really want to know about. Okay? Okay, so to really get at the weird behavior of a black hole, we can examine the causal structure of the black hole. So that is, we're going to look at light cones. Because after all, you know, if you want to draw on the space-time where you can and can't go, and that's clearly what an event horizon is dictating. Once you're inside of it, you can't leave. If you want to illustrate this, you should just consider the light cones. Right? Remember, on a flat space-time, if I have a point here, the light cones come out like that. That means this event, this point, can go anywhere inside. If it happens to be light, it moves along the edges. Okay, but if I ask, where can this thing go? It can go in the future light cone. Okay? Obviously, the light cones are not going to be this simple. So let's explore the light cone representation of what's going on. So remember, a light cone is defined as a path which has the length, Nick, Kiana. Gus? Oh man. Sam!
I think they're trying to talk. I don't think we can hear you.
Okay, we must have the. Hold on. Sorry, folks. I think I have the volume turned down. I don't know how. I don't know how I turned the volume up. Try and talk. Anyone talk. Oh man, I'm getting a chat. I bet they're saying.
You're muted?
Oh boy. Okay, I can't hear anything that y'all are saying. Let me try this. Can you hear me? Keep talking. Keep talking.
I appreciate you can do theoretical physics versus Zoom.
Keep talking. Oh man. Maybe they can view on this. No, this doesn't have. No, this is just the camera. Okay, I am so sorry, folks, but I can't hear you.
Is it going through the system like a computer and just not the system?
So this is not muted. I don't. Oh, so you're saying is the computer muted?
There's a chance it's going through the computer.
Try it now.
Can you hear me now?
Yes, we can.
Hell yeah.
We were wondering why you people were being so damn quiet, but now we understand why. Sorry about that. Anyway, Kiana, I was trying to ask you a question.
Yeah, what was the question again? Sorry, I'm not sure.
That's fine. What is the length of ds squared if you're looking at light?
Speed?
Say it again.
Speed?
That's this. I'm doing a dance. Can you? Oh, sorry.
PT?
This is CT. I'm doing.
Zero.
Zero. Yes, thank you. Woo. Yes.
Oh, okay.
Yeah, no, don't worry about it. Okay, it's so nice to have you guys on. Sorry about that. Okay, so I need to pick up the pace. I'm never going to finish this. So in fact, I'm not even going to write down the full names. I'm just going to write down Schwarzschild and Eddington Finkelstein. Okay, so let's look at what ds squared equals 0 implies for Finkel. Woo! Yes, 1 minus 2gm over r dt squared plus 1 minus 2gm over r inverse dr squared, where we're going to think about radial motion only. Okay, so we don't care about angular motion of light. Don't worry about that. And then for the Eddington-Finkelstein, we have minus 1 minus 2gm over r dv squared plus 2 dv dr. Okay? Now, for the Schwarzschild, here's what we're going to do. I'll do it here. Okay. So first of all, for the Schwarzschild, taking this and extracting dr dt from it, what we find is plus or minus 1 minus 2gm over r. Okay? That makes sense? All right? And what I want you to notice is that this goes to plus or minus 1 as r goes to infinity. That's pretty simple. But it goes to 0 as r goes to 2gm. Okay? So what this means is that as r goes to infinity, as you get hella far away from a Schwarzschild black hole, light travels at the speed of light, with the speed of plus or minus 1. C is 1. However, at r equals 2gm, light is traveling at 0. Huh. That's weird. Okay? So in order to illustrate this, what we're going to do is we're going to flip it. We're going to do dt dr, which is of course just 1 over this. And this will let us solve for t as a function of r. Plus a constant. Okay? So now if I want to plot this, what I'll get is the following. And I guess I can plot it down here. Okay, I did dtdr because I'm going to draw curves with a function t depending on r. So this is the slope of the curve. That's what it's telling me. Okay? So first of all, there is this critical point, r equals 2gm, where things are going crazy. If I'm near r equals 2gm, well, actually, let's go far away first. If I'm far away from r equals 2gm, if I'm at r equal infinity, we know that the light cones are going to open up at 45 degrees, okay, because we've taken the speed of light to be 1. So the slope dtdr is 1, or minus 1, okay? However, as we get closer and closer to r equals 2gm, what they're doing is they're folding up. And at r equals 2gm, both of them are pointing straight up. Okay? So in the Schwarzschild coordinate description, what's happening is the light cones, as we move towards the horizon, are closing up such that when you get to the horizon, the only way you can move is in time, not in space. Which seems to imply that you can't even pass through the horizon. I mean, you come to rest at the horizon, so what the hell? But remember, these are not good coordinates. Eddington, Finkelstein are way better, okay? Now, of course, we can follow the trajectory of these, and what we find is that they arc up, because as I get closer, the light cones have to close up. Okay, that's going to be an important observation in a bit. Okay? So this sucks, so let's try the same thing with Eddington-Finkelstein and see what Eddington-Finkelstein has to say. So for Eddington-Finkelstein, it turns out that we have a variety of possibilities for null trajectories. Okay? So now if I take this and I want to find the slopes, what I find is the following. First of all, one possibility for satisfying this is for dv to be 0. Right? If dv is 0, then this is 0. Okay? But that tells me that v is constant. Right? Make sense? Of course, I just erased it, so I'll have to write it again. But v is t plus r plus 2gm, natural log of the absolute value of r over 2gm minus 1. Okay? So the solution to the trajectory of a photon, one solution is dv equals 0. And what's important here is as t increases, r must decrease in order for this to remain constant. Okay? As t increases, r must decrease. And it doesn't matter what value of r you're at. Doesn't matter if you're at r bigger than 2gm, less than 2gm, it doesn't matter. Okay? Now, there's a second way to satisfy this, and that is to say, if dr is 0 and r equals 2gm. Okay? If dr is 0, obviously this term is 0, and then if I also take r equals 2gm, this is 0. Everybody see that? So at dr equals 0, that is if I am at a fixed value of the radius, and I happen to be at the radius 2gm, then I am satisfying the path of light. Okay? This means it's radially stationary. Okay? You're not moving to a greater or smaller radius. And then last but not least, we have C, where we say dr dv is 1/2 1 minus 2gm over r. And this is greater than 0 when r is greater than 2gm, and it's less than 0 when r is less than 2gm. Okay? Well, think about it. dr dv, this is outgoing, and this is ingoing. Okay? So summarizing, here is what these things are giving us. We have the singularity at r equals 0. We have the horizon at r equals 2gm. And then inside of this radius, we have ingoing trajectories which are due to solution A. Okay? At the horizon, we also have ingoing trajectories which are due to solution A. And in fact, outside of the horizon, we have ingoing trajectories which are due to solution A. Because I told you A implies that T is increasing, that makes R decrease, and that R value doesn't matter. You can be outside, inside, or on the horizon. Okay? Now, for answer B, we have a stationary point on the horizon. That is a point at which you're not moving in or out. And then we have that the answer from C is that if you're outside of the horizon, you move out. And if you're inside the horizon, you move in. Okay? Now, I want to point out to you, A is obviously an inward directed trajectory because you're going towards the source, even if you're external. That's the same when you pass through the horizon, it's the same when you're inside. C is representing an outward going trajectory, but inside of the horizon, it doesn't matter. You can try to go out. You will still go towards r equals 0. Now to make this clear, let's plot the light cones. So in order to plot the light cones, we're actually going to make use of a definition of time which is Schwarzschild compatible at infinity. So if we use v minus r for our time definition, this is just going to agree because t goes to t as r goes to infinity. Okay? So now if I plot the Eddington-Finkelstein coordinates with t twiddle, what we find is, of course, we have this special value of the radius at 2gm. If we're very, very far away, then the light cones open up at 45 degrees, as usual. Okay? And now we see what's happening. As we move closer to the horizon, the inward trajectory A is always going to be traveling in the same direction. So the arm of the light cone is, I'm doing it right, is always going to be at 45 degrees. Okay, these are from solution A. And I'm sorry, I'm really bad at drawing things accurately when they're low on the board because I'm a tall guy. Okay? However, if I think about the answers B and C, what I find is as follows. Exteriorly, what happens is the outward going light cone gets ramped up and up and up until at this point I get answer B. And then once I'm inside, I go back to answer C. Now think about it for a moment. A light cone defines where you can go. What is this light cone telling you you can do?
Escape.
This light cone tells you you can go in or away. What does this light cone tell you you can do?
Stay or go.
Well, if you're light, you can stay. If you're not light, once you touch this, you're done. What does this light cone tell you you're going to do? You're going to head towards the zero. Okay? So, Eddington-Finkelstein are basically, instead of saying that the light cones are closing up, which is what's generating this coordinate singularity, they're giving us that the light cones are simply tipping over as we pass through the horizon. As we pass through the horizon, there's nothing which is arbitrarily shooting to infinity. Okay? And of course, we could continue these, but in this picture, the inward going trajectory is always at 45 degrees. The outward going trajectory just relaxes to 45 degrees, except here, where it must go there, and then here it relaxes to 45 degrees, coincident with the inward going trajectory. Okay? So now I'm going to finish up. Are there any questions before we move on? So hopefully you can appreciate the fact that A, this metric in these coordinates, not good for the job. Okay? We did discover that this, even though it looks bad in these coordinates, this is not bad. It's not a curvature singularity. This is. Okay? However, by redefining the coordinates, we showed smoothly that this is fine, except for this very interesting behavior. And by the way, it's really interesting. You know, you started out knowing a black hole. You know, there's a singularity in the center, and then there's this event horizon. Once you go past the event horizon, you can't turn around and come back. You remember that? You had a picture of a black hole in your head before you saw this math. That's not the way it went in history. In history, they did all of this math, and they eventually got to this picture where they said, shit, once you're past here, there's no going back. And notice, there's no going back at all. You can't, once you're here, you can't go there. You can only go to smaller radius. And this is in contradiction to the Newtonian black hole, which we talked about last time. Okay, so I'm going to finish up with yet another use of these diagrams. And next time, how many of you are impressed? Nobody? Okay, next time, I will impress you. Next time, we're going to take this to a place which you've probably never heard of. At any rate, what I'm going to do now is I'm going to show you what you see if you throw something in and you stay out. Okay? So, now I'm going to draw my graph up here where I can actually draw. Imagine, I'm going to use Eddington-Finkelstein coordinates since they're the best. So we've got this wonderful horizon. 0, the bad boy. All right? Now, way out here, we know that the light cones open up at 45 degrees. Never draw 45 degrees. Well, that's 45. Okay? So now what we're going to do is we are going to take an observer who is at a fixed value of r, well outside of the light cone. Or, sorry, well outside of the radius, or the event horizon. Damn. This is killing me. Okay? So we're going to take an observer who is just sitting happily at the same value of r. Okay? And then we're going to let him throw something into the black hole. And we know that it just has to move inside of the light cone. He could throw a beam of light in, it doesn't matter. So his path will increase, 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 and eventually go to the 0. All right? First of all, I want you to notice, passing through the horizon of a black hole, nothing dangerous there. It's not highly curved. Hitting the singularity at r equals 0, that kind of sucks. Okay? But now I would like to ask, well, this guy took his buddy and threw him in. What does he see? Okay? Well, one of the things that we know is that his buddy's heart beats. And his buddy is super brave, so his heartbeat is actually pretty damn regular as he goes through a black hole. And it's funny because when you're doing this kind of dotting, you pick at the very beginning how far apart you're going to do them, and you do them really close, and you're like, shit, I got to draw a lot of dots. I'm done! Okay? And then each of these is regular. So we can say this is delta t1, and maybe this is delta t. So I'm going to call this observer 2 and this observer 1. So this is delta t1, that's a delta t1. These are all just delta t1s. Delta t1s are the heartbeats of the observer as they go into the black hole, as perceived by the observer. I'm feeling a heartbeat. Boom, 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 boom. Okay, this is my heartbeat. The question, though, is, if he's listening to it, what does he hear? All right? Well, remember, heartbeats travel at almost the speed of light. So they're going to go up towards him, and they're going to hit him. But as he gets closer and closer to the black hole, shit, my pictures. I got too many heartbeats on here. Sorry, folks. I gotta reorganize this because I can't do what I want to do. So let me redraw this very quickly. There's my path, and then I'll be a real thumper. There we go. That's what I'm talking about. Those heartbeats I can monitor. Okay, at any rate. So this is delta t. This is delta t. Okay. Here, this thing is so far out, the heartbeat travels at the speed of light to the observer. Here, it's just starting out that way, and then it gets to the speed of light. Here it's doing that. Here it's doing this. What's happening? My very regular heartbeats are being perceived as farther apart. Okay? This is my friend's notion of delta t2. This is my friend's delta t notion of delta t2. When I get to the horizon, what does he hear? How much delta t, how much is delta t for the, actually it's a single beat, so I can't do a delta t. So a better way to do this is just to have him shine a light at me. Okay, now we can talk about the frequency of the light. So what happens to the frequency of the light as he moves towards the horizon?
It goes to 0.
It redshifts to 0. Okay? Now what I want to point out is the light is not redshifting. The light is being emitted at the same frequency. It is the perception of this observer which is saying, oh, he's fading out. Okay? So it's interesting, when someone throws someone into a black hole, there is this argument that the person never gets to this point. They kind of get frozen at the horizon. Okay? However, you can't just get frozen at the horizon and you're like, I'm stuck on the horizon. No, you also fade to zero because all of the light is redshifted away. You are emitting light the whole way in. But two things are happening to this observer. You're slowing down as you get closer, and the light is redshifting away. Okay? Now, this is obviously something which is the combination of both general and special relativity, right? Because if something is moving, time dilation says that the interval of time between, or of heartbeats, is going to be different. And you are moving here, okay? So you do have a change or a dilation of time due to the motion, but in conjunction, you have the time dilation which is owed to the geometry. Okay? All right, that's it for today. Once again, I will fascinate you when we meet next time. I think I'll blow you away, actually, a bit. But sorry again for the quiz. If it was hella hard, you know, we'll go easy on you on the grading. I will see you all on Thursday. And I do want to point out that that is, yeah, that's officially our E-Days lecture. And I don't know what you've heard, but I want you all to be well behaved. You can stop it.